In this example, we demonstrate how to construct a simulation model with native Excel functionality using the Sanotronics example. Sanotronics LLC is analyzing the first-year profit potential of a new medical device. Profit is computed by taking price, subtracting off the direct labor cost per unit and the parts cost per unit, and multiplying this term by the demand, and then subtracting off the advertising and administrative costs. The selling price per unit is known with certainty to be $249, and the administrative and advertising costs are known with certainty to be $1 million. However, the other three parameters, direct labor cost per unit, parts cost per unit, and first-year demand, are not known with certainty. The possible values for the uncertain parameter direct labor cost per unit are $43, $44, $45, $46, or $47. The relative likelihoods of these 5 values are given by the heights of the bars in this chart. There is a 10% chance that direct labor cost per unit will be $43, a 20% chance that it will be $44, a 40% chance that it will be $45, a 20% chance that it will be $46, and a 10% chance that it will be equal to $47. You see the sum of these heights will equal 100%, and so therefore this defines a probability distribution. The possible values for the parts cost per unit are described by the uniform probability distribution. In this case, parts cost are equally likely to be any value between $80 and $100. The demand for the new medical device is given by a normal probability distribution with an average of 15,000 units and a standard deviation of 4,500 units. This spreadsheet contains the Sanotronics model for computing the profit corresponding to first-year sales of a new medical device. And cells B4 through B8 contain the current values of the 5 parameters. The selling price per unit is set at $249. The administrative and advertising cost is set at $1 million. The direct labor cost per unit is set at $45. The parts cost per unit is set at $90, and the first-year demand is set at 15,000 units. For these values, the profit is computed to be $710,000 according to the Excel formula that implements the profit function. The next steps are to replace the direct labor cost per unit, the parts cost per unit, and demand with random values according to the distributions rather than fixed values. In the current spreadsheet, direct labor cost per unit is entered as $45 exactly. However, we know that this parameter is not known with certainty. Rather, we believe this parameter will range between $43 and $47 with the corresponding probabilities. So therefore, we would like to, instead of entering $45 for direct labor cost, we would like the spreadsheet to generate a value of 43, 44, 45, 46, or 47 with the corresponding probabilities. To do so, we need to take the interval from 0 to 1 and break it up into subintervals whose length correspond to the probability of the corresponding cost. for the cost of $43, which has a 10% chance of occurring, we begin the lower end of the interval at 0 and extend this interval from 0 to 0.1. So therefore, the width of this interval has width of 0.1, which corresponds to probability of $43 occurring. The second segment begins where the first segment leaves off at 10% and extends from 10%, or 0.1, to 0.3. So therefore, the segment corresponding to $44 extends from 0.1 to 0.3, which has a width of 0.2, which is the same as the probability of $44 occurring. The third segment begins where the second segment leaves off and extends by the amount of the probability of $45. So 0.3 to 0.7 has a width of 0.4 units. 46, the segment corresponding to 46 picks up at 0.7 where the previous interval left off and extends from 0.7 to 0.9. And the final segment corresponding to $47 begins at 0.9 and extends from 0.9 to 1 with the width of 0.1. Now that we have broken up the interval from 0 to 1 into segments that correspond to the probabilities of each of the costs, we would like Excel to randomly pick a cost according to those probabilities. To do so, we place the value of 45, and we want to generate a random value. So to demonstrate, if we enter the function rand into cell C6, we see that this function generates a random number between 0 and 1. What we would like to do is take that random number between 0 and 1 and place it into the appropriate interval. So for instance, if we generate a value of 0.7009, that would fall into this interval and would generate a value of 46. If we tap F9 and generate a new random variable, we get a value of 0.7281, which would also land in the interval 0.7 to 0.9 and generate a value of 46. A value of 0.481 would generate a value in the interval between 0.3 and 0.7, corresponding to a value of $45. To get Excel to do this lookup for us, we use the VLOOKUP function. And the VLOOKUP function is going to refer to this random variable value. It's going to look it up in the table that we constructed ranging from A15 to C19. Given that we look up the random value between 0 and 1 in the first column, we will then return the value in the first, second, the third column, the cost per unit column. So we type a 3 here. And notice that the value that we generated, 0.481, does not exactly equal the lower end of the interval. So therefore, we need an approximate match. And so we enter true as the last argument. This means it will find the value in the first column, which is the last value that it is larger than. So for instance, when we have a value of 0.501, we would expect that we'd return a value of 40. It's in the bin between 0.3 to 0.7, and so therefore it would return the value of 45, which it does. And if we tap the F9 key, we will see and be able to test that indeed Excel is now generating random numbers according to the distribution specified. In this spreadsheet, parts cost per unit is currently fixed to be $90. However, we know the value of this parameter is uncertain, and we believe that the parts cost is actually described by a uniform random variable with a lower bound of $80 and an upper bound of $100. To have Excel generate a value of this uniform random variable, we once again will use the rand function to generate a value between 0 and 1. And in this particular case, this random number between 0 and 1 is going to represent the percentage of the way between 80 and 100 that the parts cost per unit value exists. To do so, we first replace the value of 90 with a formula. In this particular case, we entered the lower bound of $80 from cell F14 because we know the parts cost per unit will always be at least $80. And then we add the segment of the range. In this case, the range is F15 100 minus F14 with a value of 80. And to express the percentage of that range, we multiply that by the value of the random number between 0 and 1. So we observe that for a random number of 0.279, we get a parts cost of $85.59. This value of $85.59 is 27.9% of the way between 80 and 100. Tapping F9, we get a random number of value of 0.82. This corresponds to a parts cost per unit of $96.43. This means that $96.43 is 82.1% of the way between 80 and 100. Currently, the value of demand for the new medical device that Sanotronics is producing is set to 15,000, as shown here in cell B8. However, the value of this parameter is uncertain. Sanotronics believes that the demand is an uncertain value from a normal distribution with a mean of 15,000 and a standard deviation of 4,500. Therefore, what we would like to do is have Excel generate a value from this normal distribution via a random draw. To do so, we will use the rand function to first generate a random number between 0 and 1. Then we're going to replace the fixed value of 15,000 in cell B8 with an Excel formula norm.inv. The first argument of the norm.inv function is a probability. The probability that we will use is generated by the rand function in cell C8. The next two arguments of the norm.inv function are the mean and the standard deviation of the normal distribution we are considering. When we hit enter, we will see a value generated from the normal distribution with a mean of 15,000 and a standard deviation of 4,500. To understand how this value is generated from the random number between 0 and 1, understand that for this case, the value 9,820 corresponds to the value such that there are 12.48% of the values less than 9,820 in the normal distribution with a mean of 15,000 and a standard deviation of 4,500. If we hit the F9 key, we can generate new normal random variables from this distribution. For instance, the value of 15,092 is such that roughly half, about half of the values are smaller than this, 50.81%. If we tap F9 again, we get a value of 17,167. We see that in this normal distribution with a mean of 15,000 and 4,000, standard deviation of 4,500, 68.497% of the values are smaller than 17,167. So the random number generated directly results in the normal random variable in cell B8. Now that we have established how to generate the random variables for direct labor cost, parts per cost per unit, and demand, we are ready to run a set of simulation trials and record the data from these trials. This is equivalent to tapping the F9 key repeatedly and recording the results. To do so, we set up a table of 1,000 simulation trials shown in the first column A here. In the first row of the table, we link the direct labor cost per unit to where we are generating the random variable in cell B6. The parts cost per unit were linked to B7, the demand to B8, and the profit to B11. Then we highlight the entire table and on the data ribbon, go to What If Analysis and select a data table. And in this particular case, we have the data that we are using is the simulation trial number. And all we would like to do is plug that simulation trial number into some blank cell in my spreadsheet. I will select cell D1 and hit OK. What this does is forces Excel to recalculate the simulation 1,000 times by executing a benign procedure of taking the simulation trial number and plugging it into cell D1. This causes the spreadsheet to recalculate, at which point the data table records that information. So for instance, in the second trial, the direct labor cost was sampled to be $44. The parts cost per unit random value was $80.98. The demand was sampled to be 12,537 units, resulting in a profit of $500,054 and $899. We can now take this 1,000 observed values and compute summary statistics from the profit. You take the average profit of the 1,000 observed profit values. We can compute the sample standard deviation. We can find the minimum profit out of the 1,000 values. The maximum profit. And we could also compute a percentile. In this particular case, we could compute the probability that the profit was actually negative using a COUNTIF function. So in a COUNTIF function, we highlight the range that we would like to count over and then supply the criterion. And in this particular case, we are interested in less than 0. And so we get 86 instances where there were 86 instances out of 1,000 where the profit was negative. To convert that to a probability, we just divide that by the total number of instances, which we know is 1,000, but we can also compute by using the count function. So we see here there is roughly an 8.8% chance of profit being less than 0 based off this simulation. We could also generate a distribution of the values using the frequency command. To use the frequency command, we first create a set of bins for our histogram, and then we highlight the range adjacent to the set of bins. To use the frequency command, we type in equal frequency. We highlight the range of data, the 1,000 profit values, and then we highlight the range of bins for our histogram. To execute the frequency command, however, we cannot just hit enter. We have to hold Control Shift and then hit enter. And this will automatically populate each of the count in each of the bins. So we see here that there are 3 profit values that were between -1 million and 750,000, 5 that were between -750,000 and -500,000, and so on. We could also link this data to a graph and build a chart and see the profit distribution as shown above.